Hello everyone. You made it back. Man, you really stuck with it after that long video from the review chapter. Man, you deserve a round of applause for coming back for more. No, but like I said, the next videos from here on out will be really short. I mean, compared to the last one, because it's all just one topic. For example, this section, it's called solving equations, but you're going to see that in this section they only give us the simplest equations. So this is only one page of notes, and I think that'll be plenty to get the idea. The next section, what's it called? I think it's called using the properties together. It's basically going to be solving equations where it takes more than one step to solve it. So you can expect kind of the most boring equations in this section, just where you only need to do one thing to solve the equation. But it's good, building a foundation. And I know it depends what school you went to and where you took the previous course. But some people have a really good, strong mathematical foundation and some don't. So this is a good section for those who feel like maybe their foundation's not quite as strong as it could be. So let's just jump into it so this video doesn't get too long, right? Let's see. The very beginning we have just what does it even mean for a number to be a solution to an equation? For example, in this first example here, they say x equals 5 is a solution to the equation 8 minus x equals 3. So what does that even mean, and is there a way to validate that? Yeah, that means that if I were to substitute 5 where x is here in this equation, I should get a true statement. So if I wanted to, I can go off and check that. Rewrite it, 8 minus x equals 3, but instead of where x was, I'm going to replace it with the value that they gave me, or they're telling me x equals 5, and I want to verify it. So notice that the equation they gave me and what I just wrote are the same, except where x was, I now have a 5. And if I simplify the left side of that equation, 8 minus 5 is 3. The right side's 3. That's true. 3 equals 3. That's a check, so that means that is a solution. They were right. Maybe we'll try to check it for a more complicated one. In this next example, they're trying to say that that's a typo, sorry. Notice they said m equals negative 2 is a solution to, this should be an m, sorry. I think I told you guys in the last video, I'm so boring with my variables. I was trying to mix it up with m, and I couldn't stick with it. Sorry. So imagine that was a 5m minus 7 equals 6 minus 3m. So the same thing, I'm going to replace m with the value they gave me, negative 2. It's just that this time I have two places to put negative 2 since there are two m's. So it was 5m, but again, I'm replacing m with negative 2. And I think especially when your variable is a negative value, you want to replace it in parentheses. That way you know kind of the operation between that number and the 5 in the front. And then 6 minus 3 times another m, and again, m is negative 2. So I'm going to simplify the left side, simplify the right side. If the left side and the right side are the same number, then m equals negative 2 is a solution. But if they're different numbers, then it is not a solution. So kind of with order of operations, the first thing I would do here is multiply 5 times negative 2, which is negative 10. And then I'm going to subtract negative 7. Negative 10 subtract 7 is negative 17. So okay, in order for m equals negative 2 to be an actual solution to this equation, when I simplify the right side of this equation, I better also get negative 17. If I get anything else, that means it's not a solution. Let's see, 6, okay, and then you have a negative 3 multiplied by a negative 2, that's a positive 6. 6 plus 6 is 12, that is not true. Last time I checked, negative 17 does not equal 12. That's a no, that means that that value they gave us is not a solution. Is not a solution. Yeah, the left and the right side better be the exact same number. If they're not, it's a no. Let's see. And so I think they want you to know that in the very beginning. That way, once we solve these equations, for example, this guy here, the x plus 13 is 27. If we find a solution, I don't know, just to be sure, what if we made a mistake? We can always do what we did in these above examples. Substitute the value that we got back in to make sure that we actually did everything correctly and we got the right solution. So if you're familiar with equations, you probably know this already, but you should think of an equation like a scale. So if you have a scale and it's balanced, that means there's the same amount of weight on one side as there is on the other. But if you add weight to one side and not the other, then of course the scale is going to tip and be unbalanced. So think of an equation, you don't want to tip the scale and make it unbalanced. So whatever you do to one side of an equation, say over here, x plus 13, you want to do to the other side as well, or else you're going to, it's not going to be balanced, it'll tip and you won't get the right solution. So notice they, in this picture, they tried to show how to solve it and what they're doing to both sides. But we'll just solve it over here on this area. So if you have x plus 13 equals 27, keep in mind what you want. In the end, I want to see x equals something. That's kind of my goal. So I have to say, all right, what in this equation is preventing me from achieving that goal? It's the plus 13, if you really think about it. I want x to be by itself on one side of the equal sign. That 13 is in the way. So I kind of have to ask myself, how do I get rid of the 13? I get rid of. So what do you do is just think, what's the operation that's between x and 13 right now? And then do the opposite to both sides. So right now, since x and 13 are being added, I'm going to do the opposite to both sides and subtract 13 from the left and the right side. Of course, I really only want to do it to the left side because I want to see the left side become more simplified. But I have to do it to the right side because I have to balance this equation out. Let's see. So now if you don't have to show the step if you don't want, but just so it makes sense why that did what we wanted it to do. We already had x plus 13, but now we've also subtracted 13 from the left side. And the right side is what it was before, 27, but now subtract 13. But now think about the left side of the equation here, x plus 13 minus 13. There are a few like terms there. You got the 13 and the negative 13, but of course they're going to add up to 0. So all that's left on the left side of the equation is x, which is exactly what we wanted. And on the right side, all we have to do is subtract 13 from 27 and we'll get 14. Perfect. So I think that's going to be a solution. But if you want to check, all you have to do is substitute. Grab 14 and replace it back in the original there. You can kind of do it in your head. I imagine, okay, what if this was a 14? That's 14 plus 13. Is that 27? Yes, that makes sense. So usually I usually check these in my head. But I think if I were taking an exam and I had extra time at the end, I would probably actually write it out, check it, because the stakes are kind of higher on an exam rather than your homework or something like that. Okay, that was a good one. Sorry, a lot of you guys are probably bored thinking, really? This is what we're doing? Sorry, we just, we've got to start from the beginning here. But it's kind of fun, right? Having a good time. You feel like you're solving mysteries. I don't know if you've ever seen Scooby-Doo or something like that. You feel like you're part of that mystery team, or I don't know what they're called, but I don't know. I'm trying to make it more exciting. All right, let's solve another mystery, gang. Let's see. Here we want to solve for y. It doesn't say solve for y, but it's kind of implied whatever the variable is, you're trying to solve for that guy. So in the end, I'd want to see y equals something, or actually, notice in this one, I have y on the right side. So I'm more likely to see this expression, y equals something, or, something equals y. But it doesn't really matter what side your variable ends up on, as long as it ends up by itself. So I'm thinking, kind of like in the last one, I'm thinking, okay, what's preventing me here from having my variable isolated? Is it the 24? Is it the 3? Is it the negative? It's the 3 and the negative, the whole thing. I need to get rid of that entire negative 3. So I need to get rid of it. All I have to do is ask myself, what's the operation right now between the negative 3 and the y? Well, they're multiplying. Even though I don't see an operation, like in example 1, I actually saw a plus sign. But like we said before, if you see two things next to each other, it automatically means multiplication. So I have to think to myself, okay, they're multiplying. What's the opposite of multiplying? Dividing. I'm going to divide both sides. And I don't know if there was anyone that was thinking, I was going to divide by just 3, not the negative. If you just divided by 3, yeah, you'd get rid of the 3, but you'd still have a negative y left. And you don't want to see, I don't want to know what negative y is, I want to know what y is. So you might as well knock out both the 3 and the negative at once, just to get rid of everything except y. Alright, so I think if we do that, it ends up y is by itself, because I guess, yeah, let's take an extra step here just to be sure. So on the left side, we have 24 divided by -3. That's -8. I can handle that part. And then on the right side, if you think about it, you can think -3 divided by -3. Why? So let's see, -3 divided by -3. That's 1. So we really come down to -8 equals +1y. Again, since -3 divided by -3 is +1. But then we've said this before, if you have a variable multiplied by any 1. Yeah, 1 times any variable is just that variable. So we actually have the solution without even knowing it. -8 equals 1y. So that's the same thing as saying -8 is y. So that must be the solution. And that one, if you want, again, you can write it out to check it. But I think if I just imagine, what if I put -8 right here where that y was? Then it would be, instead of -3 times y, -3 times -8. Let's see, -3 times -8 is +24. That's perfect, because the left side is +24. Yay, we checked it. Good job. Okay, calm down, huh? All right. This is fun so far. Hopefully you guys are not too bored, having a good time. And if you're bored, it's almost over. So let's see, the next one. This guy looks a little more interesting, huh? He's got a fraction in front of him. So I'm thinking, when they want me to solve for k here in example 3, I want k by itself. That's my goal. So I'm thinking, all right, this is what I want to see. Do you guys ever do that, like in real life? Say, all right, let me visualize my goals, and then let me make it happen. That's what I like to do. This is my goal, to have k by itself, and I'm going to make it happen. Now I got to think, what's preventing k from being by itself? It's the 2/3. Okay, what's the operation between 2/3 and k? I guess it's multiplication, right? So what's the opposite of multiplication? It's division. So I think what I'll do is divide both sides by 2/3. That looks good. Because then again, if you think about the left side, you have 2/3 divided by 2/3. That's 1k. So the left side's perfect. That's exactly what you want, because 1k is k. It's just now the task is to simplify the right side. So I have 6 divided by 2/3. That's kind of one of those complex fractions, because it's a fraction within a fraction. I think the best way to tackle this one is to rewrite it as, instead of 6 divided by 2/3 with the fraction bar, 6 divided by 2/3 with the actual division sign. And I think I'm getting closer to the answer. Okay, let's see. To multiply or divide a whole number and a fraction, I have to first put the whole number over 1, because a whole number and a fraction can't really interact until the whole number becomes a fraction. And now I got to remember back from the old section, to divide two fractions, I take the second fraction, flip it upside down, and then multiply. So it'll be 6/1 multiplied by the reciprocal of 2/3, which is 3/2. And I think at this point, I might as well start reducing. Although you could multiply and then reduce. I always like to reduce first. I'm going to go for it. I see that this 2 and the 6 can reduce. 2 goes into 2 once, 2 goes into 6 3 times. And even though those 3's look tempting to reduce, you cannot reduce across. All I can do now is multiply across. K is, on the numerator, 3 times 3, which is 9, and the denominator 1 times 1, which is 1. And that's a good answer. It's correct, but it's not simplified, because if you remember, we had a property from in the review video. Anything over 1 is that number, but the simplified version is just 9. Yeah, 9/1 it's correct, it just doesn't look as nice, that's all. Yeah. So I think that looks good. What do you think? Good times. So far, so good. Alright, that might have been one of the harder ones in this section, I think, the fractions. Example 4, this one, it looks so simple that it's almost confusing. I don't know if you've ever come across those math problems. They just look too simple, and it's freaking me out right now. But I want w by itself, I guess, because that's what it means to solve an equation. Get the variable by itself. The thing that's preventing me from getting w by itself is that negative. Get rid of the negative. So I guess it's almost like so simple that it's hard to even think about what to do. But what you kind of want to think of it as is, instead of just negative w, maybe think of it as negative 1w. Because remember, there were a lot of times where we had 1 times a variable and we said, oh, we might as well just write that as the variable. But this, I think it makes it more clear when you rewrite it like that with a negative 1. Now it's clear what to do, because now I can see I have a negative 1 multiplied by w. So to get rid of it, I'm going to divide by negative 1. That makes it a lot more clear. Let's see. So when I divide, 15 divided by negative 1 is negative 15. And over on the right side, you have negative 1 over negative 1. That's 1. But, 1 times a variable is that variable. So I think we're done. So the lesson for that problem is just to remember, if you want to get rid of a negative, divide by negative 1 on both sides. And if you just kind of remember that, then you don't really have to do this step where you rewrote it as negative 1w. You just kind of keep in mind, oh, that's right, I remember to get rid of a negative in front of a variable, I divide by negative 1, and you could have kind of skipped a step here and made it a little faster. So it's up to you, but this step to write it as negative 1w, that's totally optional, not necessary. But it does make it make more sense and make you realize why you're doing it. All right, let's see. So example 5, I think this one will actually learn a good lesson in this one. So I'm looking at example 5, and it kind of looks like example 3, except instead of my variable just being kind of to the right of the fraction, it's kind of involved in the fraction. But I think it might make it a little easier if I rewrite it as 9/5 times x. Is that a legal move to make? Can I do that? I think so. Because in this process that we just did, we're usually going backwards. Like if you have a whole number, I'm thinking of x as kind of the whole number. You can multiply it by a fraction by putting it over 1 and multiplying numerator times numerator, 9 times x, 5 times 1, that kind of thing. But I guess what I'm trying to do is kind of extract the x. I'd rather get the variable as far away as possible from whatever's preventing it from being by itself. So this way, I see x is next to 9/5, and I feel like, I think I can get rid of 9/5 easier than the way it looked before when x was kind of in the mix of everything. So yeah, if you ever see your variable in the numerator, just feel free to shove it off to the side and extract it so you just see the fraction all by itself. And you know what? I'm thinking, okay, at this point, this looks a lot like example 3, where it was just a fraction times variable equals something. And I'm looking at example 3, and I notice we divided by the fraction, but then it kind of became a long process because dividing both sides by a fraction, you have to flip the fraction upside down and multiply. And you know what? I noticed in the end, all we really did was multiply by the reciprocal of that fraction. And I think if I remember that, for these types of problems, I'll have a lot easier time and I'll be able to save some time. So that's what I'll do, I think, because that's what it really came down to in that last example. Multiply both sides by the reciprocal, which remember in the last section the last video I said, that's just a fancy term for that fraction upside down. So multiply both sides by the reciprocal of the fraction. That is the coefficient. I think that's the key. Again, that's really exactly what we did in example 3. It just took us a few extra steps because we divided by the fraction, but eventually, 3 steps later, we got to where we multiplied by the reciprocal. So I'm going to go ahead and do that. Think about 9/5. What would its reciprocal be? Well, it's just that exact fraction, but upside down. So I'm going to take the reciprocal, and multiply both sides by it. So 9/5 times the left side, 5/9 times the left side, which was 9/5 x, and then 5/9 times the right side, which was 27. And you notice something that I think makes it clear why this works, because if you think about the left side, I'm multiplying 2 fractions together, but those 2 fractions reduce quite a bit. The 5's reduce, 5 goes into 5 once, and the 9's reduce. 9 goes into 9 once. So when you multiply those 2 fractions, all you really get is a 1. That's 1x. So I think we're pretty successful. That knocked out that fraction. But on the right side, I got to be careful because, again, I can't multiply a whole number by a fraction until I make that whole number into a fraction. And now that 27 is over 1, I'm free to reduce or multiply. But again, I think I like to reduce first. I'm going to take the 9 and divide it into 27. Okay, let's see. 9 goes into 9 once. 9 goes into 27 3 times. So you end up getting, let's see, multiplying across. 5 times 3 is 15. 1 times 1 is 1. And I know that any fraction whose denominator is 1 is really just a whole number. So 15 over 1 is just 15. Now that's a good looking answer right there. And that one, that one was maybe so complicated that I might want to check it. I don't know if I can check that in my head, so that might be one. For example, I might go, all right, what was the original? The original equation looked like this. I'm going to see if I substitute that value in, am I actually going to get the right, something equals something, and they're actually correct. So I think from my calculations up there, I think x is 15. So I'm going to go ahead and replace it where x was in the original equation. It was right next to the 9. And then try to simplify the left side and see if you get the same thing as the right side, the 27. Let's see here. What is 9 times 15? That's a big number. 40, I think 135? I believe. There's no shame in using a calculator on that, or, using your fingers or writing it out. Let's see. So that means I want to divide. 135 divided by 5. Let's see about that guy. Let's see. 5 can't go into 1, but it can go into 13 twice. Gotcha. Bring down the 5. 5 goes into 35 7 times. Oh my goodness. It's true. I must have done it right. Whee! Okay, it's not that exciting, huh? Anyway. All right, I think that was probably the most difficult one in this whole section. So that's a good thing to remember, that if you see a fraction coefficient that you want to get rid of, this is probably a good rule to go by. You want to multiply both sides by the reciprocal of that fraction. That's the fastest way to get rid of it. You could do like we did in example 3, which is just 1 or 2 extra steps, but this way kind of cuts out the middleman. But alright, I think you're going to be shocked by how nice examples 6 and 7 are after that one. Okay, let's see. Example 6. That one, it looks so simple, I'm thinking, why is that even here? I think they're thinking that they're tricking you by putting the variable on the right side of this -3. Maybe that's what they're trying to do, I don't know. But again, if they say solve, that just means I want that variable by itself. So I'd like to see p equals bleh when I'm done. The thing preventing me from having p by itself is that -3. So let's see. Actually, this is a kind of tricky one, huh? Because I'm thinking, all right, what's happening between the -3 and the p? Well, it's addition, but if I do the opposite of addition and subtract, well, don't write this down because it's not going to work, but let me subtract 3. That's not going to work because if I combine these guys, -3 and -3, that's -6. So I just added something to both sides that it really made the left side more complicated when I'm trying to make it simpler. So I think what I have to do is not subtract, but add. I guess it's not really the fact that this is a plus, it's more the fact that I have a -3. So actually what I'm trying to ask myself here is, what can I add or subtract with -3 to give me 0? So that's what I'm thinking. Yeah, what can I add? Add or subtract, I guess whatever it is, to -3. So I get 0. Well, what plus -3 is 0? +3. That'll do it. All right. So don't necessarily go always by the operation between the variable and your number. Think about what would actually zero that out. What would get rid of that number if I combine them? But that would work. You got -3 and 3, that makes 0. Plus the p that was already there. And on the right side, of course, you had to add the 3. -5 and 3 makes -2. And then, of course, on the left, 0 plus p is p, since 0 plus anything is that thing. Looks like p is -2. All right. And I think that one you can probably check in your head. Let me see. If I get rid of all this junk here, sorry. -2. Okay, what if -2 went in there for p? Imagine this was a -2. Then it would look like -3 plus -2. That is -5, which is the same as the right side. All right. Think we did it right. We're doing pretty good here, you guys. Hopefully you're hanging on and you're not getting too bored or it's not going too fast or anything. All right, last one. And then the next section, if you want to jump into that, that'll be the more complicated equations where it takes more than one step. We'll have to maybe add and divide or add, subtract, and multiply. A few steps, not just one. Okay, but last one. In this one, the thing that's preventing x from being by itself is the 0.2. And the operation between 0.2 and x is multiplication. What I'll have to do is divide by 0.2. That'll get rid of it. I'm not really excited about dividing by a decimal, though. I'm sure you're probably feeling the same way. But again, if I want to really show my work, which you probably don't have to once you get the hang of this, I have a 0.2 divided by 0.2 on the right side. That's a 1x. Just to kind of verify to myself that I did the right operation and I'm actually getting rid of the 0.2. On the left, or sorry, yeah, on the left side though, that's kind of tough. That's -16 divided by 0.2. Okay, and if you have access to a calculator, that's pretty easy, right? But if you want to do it by hand, this is kind of a good review of how do you divide by a decimal. So if you remember, if I want to divide by a decimal number, you can, if you want to, you can multiply or kind of take both numbers and move their decimals over to the right as many times as you want, as long as you move both of their decimals the same number of times. So I guess what I'm thinking is, I don't really want to divide by 0.2. If only I can move this decimal to the right once and make it just a 2. That would be nice. As long as you're dividing, you're free to do that, but you must move the decimal on the other number to the right as many times as you moved it for the first number. So since I moved the decimal to the right once, changing 0.2 into 2, I better do the same thing for this -16. So since -16 has a decimal directly to its right, if I move that decimal over, it kind of leaves an extra space, which, if you remember, that means you have to add a 0 to it. So yeah, if I take -16 and move its decimal to the right once, it'll become -160. So that makes it a lot easier. 2 into 160, you can either do that in your head or go off to the side and try it. I ignore the negative because I know, okay, a negative divided by a positive is a negative. So I kind of already have in my mind the answer is negative. I'm just going to focus on the division. 2 can't go into 1, but it can go into 16 8 times. If I bring down the 0, 2 goes into 0 no times. 0 times 2 is 0. All right, it goes in evenly 80 times. But again, it was a negative divided by a positive, so it must be a negative. Yay! Wee, 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 wee! All right. It's not that exciting, right? But we can check. Look at that. We're under the half-hour mark. I mean, we might as well. We're all here. We're having a good time. Okay, I'm taking the original equation and substituting -80 in. Let me see if that's true. So I would go, this is another one where you got to really dig deep. I got a -80 times a 0.2. I'm just going to keep in mind that's going to be negative because it's a positive times a negative. All right, in this one, remember you multiply 2 times 80 as if there's no decimal. 2 times 0 is 0, 2 times 8 is 16. But you have to count how many places are beyond the decimal. There's one place beyond the decimal, which means you have to move the decimal to the left once. So this is 16.0, which is the same as 16. Yay! We did it! It's the right answer! Okay. Are you as excited as I am? I hope so. If not, I'm sorry, but we'll be solving more interesting equations in the next section. Thanks for tuning in, and I'll see you guys soon.